Hello everyone, my name is Alexander Thelen. I'm an astrobiology NPP postdoc at NASA's Goddard Space Flight Center, and thank you for joining me today at AbGradCon, where I'll be talking about the exploration of Titan's atmospheric chemistry and dynamical state with Alma. Titan harbors a substantial atmosphere, which is primarily composed of molecular nitrogen. There's also a small percentage of methane and molecular hydrogen, and all of these species are dissociated and recombine into a wealth of organic compounds. Today we'll be talking about mostly hydrocarbon and nitrile species, but there are also some oxygen-bearing species, such as carbon monoxide, and a wealth of yet-to-be-identified heavy ionospheric species in the upper atmosphere. Over on the right, we have a temperature profile of Titan compared to a nominal profile of the Earth, and these are remarkably similar in shape, although Titan's profile is much more extended and much colder. The study of Titan in the submillimere, which we'll be discussing today, between about 1,000 and 70 kilometers, is comparable to previous observations by the Cassini spacecraft and those from the ground in the UV and in the infrared. The combination of all of these studies allows us to characterize Titan's atmosphere chemically and dynamically, and allows us to answer some questions such as how extensive is the atmospheric chemistry and the molecular inventory of Titan, and how are these trace constituents distributed spatially and temporally. For interest to astrobiology, we also wonder, how are these species able to interact with the surface and possibly Titan's subsurface ocean? To try to answer some of these questions, we use the Atacama Large Millimeter Submillimere Array, or ALMA, which is located high in the Chilean desert, close to 5,000 meters in altitude. ALMA is comprised of 66 antenna dishes in multiple different arrays, and these are movable, which allows for baselines between 150 meters and 16 kilometers. This enables fairly high spatial resolution at these long wavelengths, and you can see that Titan is a fairly bright and compact continuum source at these frequencies, and as such, ALMA used Titan for a number of different flux calibration observations since its inception in 2011 all the way until 2017. So there's a wealth of Titan observations that are available on the ALMA Science Archive for us to use. When looking through the ALMA flux calibration archive of Titan observations, we quickly found that ALMA has a variety of capabilities that are suitable for planetary atmosphere studies, in addition to those of astrophysical and extragalactic sources. This includes the coverage of numerous molecular species which may appear in planetary atmospheres for chemistry and isotopic ratio studies. The high spectral resolution of ALMA heterodyne spectra allow for wind speed measurements through Doppler shift, and also to resolve atmospheric emission lines, which allow you to measure the temperature and the abundance of gas with altitude. The spatial resolution, as mentioned before, allows us to map these things instantaneously to look at abundance or brightness temperature maps, and the sensitivity of the array as a whole allows for new molecular detections in the atmosphere of Titan and other solar system targets. Here's a representative spectrum of Titan, which is actually obtained from flux calibration observations, so roughly 2.5 minutes on source during 2014. But even in this short integration, we can see the richness of these submillimeter spectra. Over on the left, we have a band of acetonitrile. We have these two relatively strong lines of hydrogen cyanide isotopes, the carbon and nitrogen isotopes, and then we even have some low signal acrylonitrile or ethyl cyanide transitions here. So analyzing these spectra in a number of different ways will allow us to complete some of the projects that I'll describe hereafter. And even just integrating over these spectral lines, you can obtain these nice emission maps, which will show you a snapshot view of the distribution of a given molecular species at this certain time when the observation was taken. So on the top row, we have HC3N, or cyanoacetylene, which we can see very rapidly transitions from the North Pole to the South Pole during 2012 to 2015. And this is because of the relatively short photochemical lifetime of these species. Whereas, in contrast, the bottom row, we can see CH3CN, or acetonitrile, which we showed previously, which stays at the North Pole much longer than cyanoacetylene because of its long photochemical lifetime, which makes it a good tracer of the dynamics of Titan's atmosphere. There's a few ways that we can assess Titan's dynamical state using ALMA observations. The first is through the retrieval of temperature from carbon monoxide from roughly the tropopause around 60 kilometers to the lower mesosphere above 500 kilometers. And this is because CO is well mixed in the atmosphere of Titan at roughly 50 parts per million. So here is a composition of different radio transfer retrieval results of Titan's temperature at different latitudes, which I've made into a temperature map during 2017 in Titan's northern summer solstice. So we can see a large warming that occurs at the subsolar latitudes around 26 north, but there's also warming that's occurring in the stratopause at the north polar region and the mid-southern latitudes. And this is indicative of Titan's global pole-to-pole circulation cell, which is currently lofting air from the northern or summer pole down into the southern winter pole. We can measure Titan's atmospheric temperature further up in the atmosphere using emission lines of HCN. As you can see over here on the left, these really broad features allow us to sound temperatures into the 800 and 900 kilometer range. And in particular, this absorption core in the HCN spectra allows us to infer the mesopause temperature of Titan, which hasn't really been studied in depth with latitude or with time before these analyses. So this is a preliminary result, but we're seeing already from Alma observations that the mesopause likely varies significantly in both its altitude and its temperature measurement. So this is, largely due to wave motion and changes in the atmospheric composition, which can have effects on the radiative energy budget of Titan's atmosphere. We've previously seen that this portion of the atmosphere is really variable with time from Cassini observations. Alma's high spectral resolution capabilities allow us to observe Doppler shifts in emission lines of rotational spectra, which we can directly map to wind speed magnitudes in the atmosphere of Titan. Depending on what chemical species you're observing, you can look between 300 and 1,000 kilometers in the atmosphere, depending on where the species line core is sensitive to emission. So in Martin Corner's paper from last year, we were looking at CH3CN, HC3N, and HNC wind maps from 2017 and comparing those to the published ones in 2016 from Lelouch et al., where they found a thermospheric jet in Titan's upper atmosphere around the equator. Our wind speed measurements showed a dramatic decrease over this 9-month period of about 47%, which is due to a dynamical instability or variable wave activity between the middle and the upper atmosphere of Titan, which is really cool. Now moving on to some chemistry and composition studies, which are possible from these Alma observations, we can take the temperatures that we retrieved earlier from CO and ACN and use them to do radio transfer analysis in multiple locations on Titan's disk to make these abundance maps with latitude and altitude or pressure. So on the left we have a map of cyanoacetylene with altitude, and on the right we have acetonitrile. And again, similar to the maps that I showed a few slides ago, both of these molecules have abundance enhancement towards the pole, and in particular the enhancement at the south pole compared to the equator for these species varies by an order of magnitude, which is really interesting. And the global circulation of Titan's pole-to-pole cell is also evident here in the enhancement above the south pole and the relative dearth of each of these molecular species towards the equator or the north. And maybe more exciting is the detection of new molecular species in Titan's atmosphere, which has a lot of applications for both its overall chemistry, feedback into its atmospheric dynamics, and for perspectives on astrobiology. Previous detections from our group early on included C2H5CN, which is ethyl cyanide on the top, and C2H3CN, which is vinyl cyanide on the bottom, which had a lot of interest from the astrobiology community. And last year, we made 2 new molecular detections in the atmosphere of Titan using dedicated Alma observations from 2016 and 2019. On the top, I'm showing the detection of methyl cyanoacetylene in this purple spectrum inset from our 2019 data. And this molecule, CH3C3N, is the largest nitrogen-bearing species that we've found thus far. Also has a really long name. And in contrast to this molecule is cyclopropanilidine, which also has a long name, and is the smallest cyclic molecule that we've found thus far in any solar system object. Both of these molecules have column density measurements which are far below everything else that we've found thus far in Titan's atmosphere. So Alma really is one of the best tools that we have in the moment to push the molecular inventory and the photochemical products of Titan's atmosphere even further. Finally, Alma allows us to observe many different isotopic species in the atmosphere of Titan. On the top row we have CH3D, as well as isotopes of HCN, and on the bottom row we have CO and CH3CN isotopes shown, and their respective values are printed below. The investigation of isotope ratios gives us insights into the formation and evolution of the atmosphere of Titan, and nitrogen and carbon ratios give us some insights into the selective isotopic fractionation that happens in the upper atmosphere. The D to H ratio of Titan is interesting because it's an order of magnitude higher than that of Saturn or Jupiter, and is much more in line with the oceans on Earth. Similarly, the oxygen ratios on Titan are pretty similar to terrestrial values. So in summary, this was a collection of different projects that we've been working on at NASA using Alma to observe Titan, and also now to observe other planetary atmospheres. But Alma is a really great tool to look at the spatial and temporal variations in the temperature, the abundance, and the wind speeds of different planets, and its high sensitivity allows for the detection of new complex molecular species and also isotopes. These things together allow us to examine the chemical complexity and the evolution of planetary atmospheres, and for Titan in particular, it allows us to continue the legacy of the Cassini-Huygens mission after its end in 2017 and observe seasonal changes in Titan after its northern summer solstice. These measurements will help us to constrain photochemical and dynamical models of Titan's atmosphere, and we'll hopefully get more observations that are dedicated observations of Titan in the future. Thank you very much, and I look forward to any of your questions.